Today we're going to look at salts of acids and bases. So anytime you take an acid and a base and you react them, you're going to produce a salt in water, not a slat in water. Don't really know where I got slat from. So basically you're going to get the H plus ion from the acid and the OH ion from the base. Those are going to make H and OH, which is H2O. And then the other things that are on the acid and the base, besides the H and the OH, are going to form together and they're going to make a salt. Now a salt is an ionic compound. So when we say salt, it doesn't just mean NaCl, table salt. Table salt is an ionic compound, but it's just one type. So any ionic compound is considered a salt. That salt can be neutral, basic, or acidic, depending on what it is, okay? Alright, so here's an example. You have an acid and a base, and they're making a salt and water, okay? So that's basically what we're going to be looking at. This process is called hydrolysis. When you're looking for if a salt is acidic or basic, you have to first off recall the strong acids, okay? So strong acids are going to be HCl, HNO3, H2SO4, and remember there are 4 other ones that you got to keep in mind. And strong bases are going to be your group 1A hydroxides, and remember sometimes group 2A, just depending. Alright, so to determine if a salt is acidic or basic or neutral, you must react it with water to see what initial acid and initial base, or parent acid and parent base, made that salt. Once you get the parent acid and parent base, you have to evaluate them for if they're strong or weak. A strong acid and a strong base are going to make a neutral salt. A strong acid and a weak base are going to make an acidic salt. And a strong base and a weak acid are going to make a basic salt. Okay? So here's our first example. We have Na and F, and we need to evaluate what parent acid and parent base made Na and F. Alright, so in order to determine the parent acid and parent base, you need to react the salt with water. Okay, so we got Na and F. We're going to react it with water. A lot of times it's helpful to write water as HOH so that you can see what's happening. This is simply a double replacement reaction, so you're going to swap the fronts. So Na is going to get the OH, and then F is going to get H, so HF. Alright, this is a strong base, and this is a weak acid. Okay, so that tells us that NaF is basic. Okay, because it's made of a strong base, weak acid. And you see under here, we found that. Okay, FeNO3. Alright, we're going to do the same thing. So FeNO3, you're going to react with water. Alright, again, it's a swap the fronts thing. That 3 came from Fe, so that's our charge there, and then NO3 is 1 minus, so that's a little swap and drop. Alright, so we're going to react and just switch the fronts again, so Fe is going to get OH, and if you're swapping and dropping correctly, you'd get this, but that's not really essential for being able to determine if it's a strong or weak. And then H is going to get the NO3, and we know that this is a strong acid. That's a weak base, so our salt is acidic in this case. Okay, and again, underneath we'll find the same thing here. Okay, alright, now NaCl. Alright, so one more time, you're going to react it with water. H is going to get Cl, and Na is going to get OH. Here you have a strong acid and a strong base, so that means the salt NaCl is neutral, or pH of 7. Okay, which is exactly what we find. Alright, so basic salts are when you react a weak acid with a strong base, and it's going to give you the basic salt and water. Basically, the anion of the salt, or the negative ion of the salt, is the important one to look at when determining if this is going to be a basic salt. So how can you tell if a salt is basic? Well, the first thing I would do is I would write the dissociation equation. So I would go over here and I would write this NaF breaks down to Na plus and F minus. Okay, so that means that the major species we'll have is Na plus F minus, and then of course, because we dissolved it in water, H2O. I then take both of the ions that were produced from the salt and react them separately with water. Okay, so first the F minus with water. So F minus is going to take an H, so you're going to get HF and then OH minus. So this is obviously a base because it's producing hydroxides and accepting a hydrogen ion. And then I'm going to take the Na plus and do the same thing, and it's going to make me NaOH and H plus. So this is the acid here. Okay? All right, so we know that it is going to be a, we already determined that it's going to be basic, okay? And now we can tell which one of the ions is going to play the biggest effect here, okay? So we know that it's going to be the F minus ion. F minus is going to compete with the OH minuses for the hydrogen ion. So that's why you end up with excess hydroxides, which makes your solution basic, okay? All right, so when you're looking at Ka and Kb, oops, got some stuff thrown in there. All right, so we took the two anion equation, or the two ion equations, excuse me, from the dissociation of the salts, which are there and there. Okay, so the same from the previous slide. And we write the equilibrium expressions, so the Kb and the Ka for both of those salts. We then lined them up, and we noticed that when we did, and if we multiplied them, things would cancel. So the HFs cancel and the F minuses cancel, which is OH minus and H plus. Now OH minus and H plus is Kw, right? So Ka times Kb is Kw. So if you know Ka or Kb, you can find the other one by using Kw. All right, so to find the pH of a salt, there's a couple steps that we're going to follow. We're first going to write the dissociation equation for the salt. Then we're going to write the reaction of each of the salt ions with water, as we did before. We'll determine the missing K value, so whichever K we're not given, we will find the other. We'll ice it, and then we're going to calculate the pH from either the H plus or the OH minus ions. Okay, so Ka is going to tell us Kb. All right, so here we have a 1 molar NaF solution, and we're given the Ka of HF. And now we need to find the pH of this solution, okay? So when you're looking at this, you need to follow your steps. So here's our first step. Well, actually, that's not our first step. I don't like that. So we'll just cross it out. Haha. All right, so first we're going to write this association equation. So we got Na plus and F minus. And then you know that you must take each of those and react them with water. Okay, so that's going to give us our HF and our OH minus, and then the Na is going to make the NaOH and the H plus. Now, how do you know which one to focus on? Well, you need to know if you expect NaF to be acidic or basic. If you can't remember that, then you need to react him with water to see what his parent acids and parent bases are. So his parent acids and parent bases were this. Okay, so strong base, weak acid, which tells us that this is going to be basic. So we want this equation because it's the one where we have a basic thing going on. Okay, all right, so with that we now need to ice it. So let's go ahead and try to ice this to determine what we got going on here. Okay, so I'm going to write this over here so I'll have a little bit of room to write an ice table since I have not left myself very much room. All right, so we got 1 mole, or 1 molar NaF, and we know that's going to dissociate completely. So we're going to get 1 F minus ion. Water is a liquid, so it doesn't count in the ice table, and you're starting with 0 of these. So that's going to be minus x, and then x, 1 minus x. Now this is in terms of hydroxide, so that's the Kb. We were given the Ka. So to find the Kb, we have to do Kw divided by our Ka. So we really have 1 times 10 to the negative 14th divided by, maybe, 7.2 times 10 to the negative 4th. Okay? All right, when you divide that out, you get a value for Kb. So 1.39 times 10 to the negative 11th. All right, so that's our Kb value. Now we need to write our equilibrium expression here, so we're going to have HF and OH minus on top because it's always products over reactants. And then 1 minus X on bottom. Now that's equal to our Kb, which is the 1.39 times 10 to the negative 11th. Now because that number is so small, we can just cross out this minus x. So it's really the square root of 1.39 times 10 to the negative 11th. So when you get that, you square root that, it'll give you your value for x. Okay, so your x value here is 3.73 times 10 to the negative 6. Okay, now that's your hydroxide concentration. So if you negative log this, then you can get the OH, the POH. Okay, so if you do negative log, it'll give you a POH of 5.4. Let's see, 5.43. All right, and then 14 minus that is our pH. So 14 minus 5.43, and we have 8.57. Now this is good news because we knew that our salt should be basic, and 8.57 is definitely in the basic range. So that's good news. Okay, all right, let's look at one other problem like this. All right, so we're going to do the same thing, but now we're going to use an acidic salt. Okay, so we're going to try to determine this. All right, first we need to determine if we think it's going to be acidic or not. And I know you already know that answer, but you won't always be given that information. So to find out, react it with water. Okay, so you're going to get HCl and NH4OH. Okay, so this is a weak base and strong acid. So we know that it should be acidic. Okay, all right, then you go and you write your dissociation equation for the actual salt itself. So we got NH4Cl dissociates into NH4 plus and Cl minus. All right, then you're going to react each of these with water. Oh snap. My pen's doing interesting stuff here. All right, so that gives you H3O plus and then NH3. All right, and we know we're looking for the acidic, so we can go and stop there because that's the one we need. 0.4 is our concentration of our salt, so that's that. Water doesn't count. These are 0. And then when you start plugging in your ice chart, you're getting this. So you really have x squared over 0.4 minus x, and I'll post these